Welcome to JOG 1400 Digital Geographies. My name's Lex Comber and I'm going to give a final talk on data and statistics in this lecture. And what I'm going to try and do here is to make sure that we're covering the practical work of weeks 18, 22 and 23. And really what I'm trying to do here is to sweep up some of the issues around that have been covered in those weeks. Okay, so if you recall that the main aim of this, one of the main aims of this module was to get you used to handling data, and the module survey was collected to help us do this. And the RStudio sessions analysing that data were to provide you with data handling experience. However, due to the strikes and now COVID, this has all been a little bit fragmented. So what I'm trying to do in this session is to pull all of the main points together. And for this reason, this lecture and the practical is split into 3 parts, each of which emphasises a key point, which together should build towards an overall understanding of data and data handling approaches. Now the 3 parts really are, towards ultimately doing some kind of analysis of your data. But before we do that, we need to know how good the data are, what are the properties in the data, what are the trends and relationships, what's the structure of the data, and are these relationships and patterns and properties, are they significant? So if we see something that's interesting, is that something that might have happened by chance? And being able to answer these questions is a core component of any data analysis that you'll undertake in the university as part of your degree and in your future lives. You need to be able to answer the questions of whether the data is usable, can you trust it? What is the data saying? And are the things that you observe statistically significant? Now, significant in this context has a particular meaning in relation to data. In part 3, we'll do some statistical tests. And statistical tests come with a measure of confidence in the test. And this is often expressed as a p-value, a probability. And what we're interested in are p-values less than or equal to 0.05. And this is referred to 95% confidence. And this is an accepted statistical benchmark. So you'll often hear people talking about if someone says that something is statistically significant, what they mean is that the relationships they found wouldn't have happened by chance. In statistical terms, it means that the results would not be found from data drawn randomly if it was drawn 95 times out of 100. That is what 95% confidence means. And so the p-values tell you that the probability of finding that relationship by chance. So the smaller the p-value, the less likely it is to be found by chance. So a 95% confidence is 95 times out of 100, and that would be 0.05 p-value. A 0.01 p-value tells you that it wouldn't be found by chance 99 times out of 100, and 0.01 is 0.001 is 99 times out of 1,000. And we often see p-values reported as 0 or as e to the minus 17, which means that there are 17 zeros after the decimal point, and that it's extremely unlikely. So really what we have then in terms of what significance is a measure of statistical surprisingness. How surprising, it gives you a measure of how surprising the result is. And this has strong links to the null hypothesis, which we'll talk about later. Okay, so the 3 parts, just to recap, are how good is my data, what are the properties, and are the properties and the relationships, are they saying something significant? And part one is we're going to recap what we did in week 18, which was all about sampling, avoiding bias, and generating some measure of the quality or representativeness of the survey data. Part two is all about examining distributions, correlations, and what's called data structure, and that is how different variables interact with each other. And these will be done using a short RStudio practical. And finally, we're going to look at whether these patterns and relationships are saying something significant, and we're going to use some statistical tests to examine those. And again, there's a short R practical. Now, how you should progress through this lecture is in one video, and then but it's in 3 parts. And each of these parts provides a short introduction to the concepts, and then there's a corresponding component in the RStudio practical. And if you haven't got RStudio installed on your computer, then you can use RStudio Cloud, and you'll need to register an account for that to do this. So what you should do now, I suppose, is download the practical PDF from the VLE, and this has all 3 parts of the practical in one document. Download the data from the VLE and put it into a work folder that you'll be working from RStudio. And open our RStudio Cloud or your own version and log in. And what I suggest you do is watch each part of the lecture in turn and then pause it. And I've put some slides in that say pause, and then do the corresponding part of the practical in RStudio. And then when you finish that, go to the next part of this, the lecture, keeping RStudio open, and then coming back to it for the second part, etc. So first, let's recap what we did in week 18, examining how good my survey is. Okay, and we talked, the lecture in week 18 talks a lot about sampling, and it emphasised the point that samples are useful, and we undertake them because we can't get access to the whole population. We often want to say something about the population, but for very practical reasons, we haven't got access to them. And this might be for cost, we might not have enough time, the population might not be available, we haven't got the resources for it, and so on. So what we do is we undertake a survey, a sample survey, and what we then do is, with the aim of analysing the sample survey data and making some inferences or predictions across the population. So the key things in the sample are avoiding bias and ensuring representativeness. Have we captured the key groups in our survey, in our population, our target population? Now, one of the things we did was to introduce the idea of a standard error statistic, okay? And what this does is generate a measure of the representativeness of a variable, okay? And it evaluates the mean of that variable. So let's consider the variable height, okay? And we have a variable in our data called height, but we don't know how representative that is of the whole population. And we can use sample statistics to evaluate the height data. And the standard error of, let's say, mean height tells us how accurate or reliable that mean is likely to be when compared with the true population mean, which we don't know. Now, this tells us, the standard error not only tells us about mean height, it also gives us a measure of the reliability of the sample and thus the survey. So we can get some indication of how good our survey is by examining the standard errors. A small standard error tells us that the sample is representative, or is likely to be representative. And we can also calculate confidence intervals of the sample mean to tell us what the true value of the mean is likely to be. What we will find is that as our sample gets larger, as n increases, the confidence intervals get nearer to the sample mean. They get closer to it. So the confidence intervals decrease with sample number, and this is the law of large numbers. So if you have a look at the practical is called practical9.r, not practical.r. Sorry about that. In that, we have a look at the effect of sample size and just looking at the impact of sample size on the standard error. And the plot shows that the standard error decreases with sample size. Now, obviously, different variables will have different standard error values. So this is for height, which had a mean of something around 170 centimetres for you guys. And if we were looking at, I don't know, hours spent in the gym, where the numbers were themselves lower, then obviously the standard error would have a different range, different possible range. So in summary, we use samples because we can't access the entire population. We need to be aware of the potential for bias in sampling, and there are some examples in the week 18 lecture. And we need to think about what our population is. So actually our survey data, we could say is the population, although not all of you undertook the survey. I think there were nearly 80 respondents, which ended up with 70 observations when the data had been cleaned. Here the population is first year undergraduate geography BA students at Leeds in the academic year 2019 to 20. But the key thing is that we want to know how reliable is the survey data. And standard errors can help us do this. Standard errors of the sample means tell us how reliable it is, and the smaller they are the better, and they will get smaller as sample size increases. And we can use confidence intervals to indicate the reliability of the sample statistic, such as mean height. And the confidence intervals give us the range within which the true parameter will be found. So not the true parameter of the sample mean, but the true parameter of the population mean. So in this case, our sample mean height was 172.02 centimetres, and the confidence intervals indicated that the true value of the population sample mean would be between 170.07 and 173.97 centimetres. Now, generally, a sample size of 25 to 30 observations is enough to capture the variation in any population. And you should perhaps remember that when you are thinking about collecting some data for your dissertation or doing some statistical analysis of a survey and so on. And there's a really good, accessible overview of standard errors and standard deviations in the link I've put up there. So just to recap, this part of the lecture and the associated practical is all about sampling, thinking about bias, but particularly generating some measure of the quality or representativeness of the survey. Now, what you should do now is go back to the VLE and start working in our studio through part 1 of the practical, and then come back to this lecture when you've completed part 1. The second part of the practical is, and the lecture, is all about understanding the properties of the data. Okay, what we're interested in is kind of examining, identifying interesting, potentially useful trends. So in the first part of the lecture and the practical, we've established that we've got a reasonable sample of the population. We're happy with the standard errors. And now we can start examining the data properties. Now, the survey data has different types of variables, And there are lots and lots of different kinds. There are categorical, numeric, counts, text, dates, and so on. But really what we're interested in is two basic types: numeric data and categorical data. Now, numeric data may be continuous or it may be counts. And categorical data may just be groups, male, female, or it might even be ordered, such as birth month, which could be ordered from January through to December, or it could be ordered from September through to August, perhaps to represent the ordering of the academic year. And we can examine the individual variable properties in different ways. So for numeric data, we can use summarizing functions such as summary and 5num. And we can see here that these give us numeric summaries of the data. So summary returns the range of the data, the max and the minimum. It returns the first and third quartiles, the median and the mean. The median and the mean give us a measure of central tendency, and the first and third quartiles give us an indication of spread. And how this works is that if you think about the mean as the 50th percentile, so if you had 100 observations of, say, height, and you laid them all out in order from the lowest to the highest, and you counted along to the 50th one, that would be the median. Okay. Now, if you counted to the 25th, that would be the first quartile. And if you counted to the 75th observation, when they're ordered in that way, that would be the third quartile. If you had 200 observations, the median would be the 100th observation. First quartile would be for the 50th one, and the third quartile would be the 75th, and so on. Now, the 5num function reports these. It's the same as summary without a label, but doesn't report the mean. Okay. Now we can also examine these numerically. So if we look at box plots, we look at handspan and hours in the gym. We've got two very different variables, very different properties there. We can see the box plots actually provide visual summaries of the same information that is returned by the summary function and the 5num function. Okay, the black bar in the middle of the box plot is the median, and the box around the black bar are the quartiles. And then the lines going out are called whiskers, so these are often known as box and whisker plots. And the whiskers indicate the 95th percentile of the distribution, where 95% of the data lies. And the dots outside of that indicate the outliers, the values that are outside of these. Now we can see here that although handspan and hours in the gym in the two box plots we can see here that they have very different properties. So if you just look at the range for handspan, we can see that the median value is much closer to the centre of that range, okay, around 180, whereas hours in the gym, the median values much closer to the left-hand, the lower end of the range. Now this starts to suggest what the histograms might look like for these. We can see that one perhaps has a more normal distribution and one has a distribution that's bunched towards the left-hand side, hours in the gym. And indeed, when we plot the histograms, we can see that. So we can see the spread of values in the data. Handspan has what's called a normal distribution, and is perhaps suggested that this is a continuous variable, whereas gym hours has a more skewed distribution to the left-hand side that's more typical of a count variable, and counts and continuous variables behave very differently. We'll come to that in a minute. But if we can now impose the summarizing the numbers from the summarizing functions onto the histograms, and here you can see the range, the quartiles, okay, and the medians. And we can see that these are much more evenly distributed for handspan and much more bunched for gym hours. And this raises an important point. Continuous variables are those which have no theoretical underlying limit. Okay, so in theory, handspan could be take any value. Okay, there are going to be biological limits, but variables that are continuous that can take, with no theoretical underlying limit, tend to have normal or bell-shaped distributions. Whereas count variables, which are limited, there are only 24 hours in a day. There are only so many people that live in a census area, tend to have skewed or what are called Poisson distributions. And we're not going to go into different types of distributions in great detail. But really, this is something to be aware of. If you see a distribution that has that kind of shape, it's typically a count. If it has a Poisson distribution, it's typically a count variable. Okay, so there are some important distinctions between numeric data, and the most important is the difference between count variables and continuous variables. And we can look at all of the data. We can see that all of the numeric data has different properties, and some of those are more or less surprising than others. I won't dwell on these. We can also fit density curves to those as well to show those distributions in a perhaps more intuitive way. And again, these shapes tell us something about the distribution of the data. Look at IMD, that's very heavily skewed to the right. Gym hours, as we know, is skewed to the left. And survey minutes looks like it's skewed, but that just could be the effect of outliers pulling the data around. I think some of you must have left the browser window open for a long time when you completed the survey. So we've looked at numeric data. We can also look at categorical data, and we can do this using the table function. And what we're interested in here is the count or frequency of each class. So looking at your travel mode, we can see that there are different counts for the different modes of transport to the university. Okay, and we can arrange this in different ways. Perhaps this is a little bit more intuitively using the as.data.frame function wrapped around table. And this gives us a nice little table of values and their frequencies. And we can look at other variables as well, and we can also count proportions. We can also determine the proportions that the frequencies represent as well. Now, we can examine these using bar plots, and if we see here that we've kind of created a variable called tab. Okay, here's table of the visual counts, the different types of contact lenses, eyeglasses or none. And then we can actually use that in a bar plot. Okay, and we can arrange the bar plots so that they're vertical or horizontal, and we can shade them. And this gives us a nice visual summary of the tabular data. Okay, this is a nice intuitive way to kind of visualize count data in categories, frequency data of categories. So as well as numeric data, which can be continuous or counts, and categorical data representing groups or classes, we can also examine how multiple variables interact. Okay, we can look at continuous to continuous, categorical to categorical, and continuous to categorical. So if we look at the first of these, this is probably the classic interaction between two numeric variables, two continuous variables, is we can look at, we can plot these together. And in this case, we've looked at height and shoe size. And there looks to be a fairly strong relationship between these, perhaps understandingly. We can quantify that relationship using a correlation statistic, a correlation measure, using the core function in R. And this tells us that there's a correlation of 0.765. It tells us that it's positive and that it's fairly strong. A correlation of 1 would be a perfect positive correlation, and a correlation of -1 would be a perfect negative correlation. Correlations range between -1 and 1. Okay, so we can see that there's a good, strong correlation, and indeed that our visual summary is confirmed by the correlation statistic. Now we can look at multiple correlations across multiple pairs of variables, and we did this in the introductory session to R. And here we're looking at the correlations between 4 numeric variables, and we can see the relationship between shoe size and height of 0.765 as before. But we can also see that there's a kind of nice, interesting negative relationship between shoe size and piercings. If the larger your shoes, the fewer piercings you have, or the more piercings you have, the smaller your shoes. And this perhaps relates to height as well. Other than that, the other correlations are relatively low. Typically, I'd be interested in correlations of 0.2, 0.3 and above. Okay, and that tells me there's something interesting going on in a pairwise way between two variables. And the plots, then we can plot these all together, and we can plot them with or without a trend line, as is demonstrated in the practical. A second kind of interaction is between different sets of categorical variables. So here I've given 3 examples of gender against visual, gender against travel mode, and gender against driving licenses. And essentially these are called correspondence matrices. Okay, it's the classic way of examining the interaction between 2 categorical variables is to do essentially a table of counts, and these are called the correspondence matrix. And again, table is used to do this, and you notice now that table, instead of just taking one variable, takes 2 variables and plots them against each other. Okay, and we can see that these are fairly interesting, potentially, there are potentially interesting differences between these. And of course we can calculate proportions. Now, perhaps of most interest is how continuous variables, numeric variables, vary with categorical ones. How do the properties of different groups vary? Okay, what are the distributions within and between groups? So the first box plot there shows the height when examined across the grouping, the gender grouping. And unsurprisingly, we can see that the typical height of male respondents is greater than the typical height of female respondents. But we can also see the same data split across socioeconomic classes, in this case the output area classification, which is described in the practical. Okay, this allocates each area to a class, and when you gave your postcodes, I used that to link to the data set to pull out the label of the class of your home residence. And we can see that, for example, the median value of height for suburban living is greater than that for respondents from industrious communities. Now, is that saying something? Is there a difference? There is a difference. I can see there's a difference. And we perhaps, there may be, it looks like there may be counting issues there, with perhaps fewer respondents from industrious communities, and suburban living, if you look here, has quite a large spread. The quartile range is quite large, whereas this is quite narrow. Now that could indicate that everyone's behaving in the same way in that area, or that could be due to a low number of counts. However, we can see that there are differences in height between the different groups. And we can also examine these numerically, and we can, these are all the potential categorical groupings here: blood donors, diets, left or right-handed, whether you've got a job, state secondary school or not, etc., etc. And we can use these to examine the differences in these numerical distributions between the different data sets, between the different groups, I'm sorry. So, data is generally of one of 2 kinds. It's generally numeric, or it's or a text or character of some kind representing some group. And we can explore the properties of data and variables using numeric and visual approaches with the aim of trying to understand the data, what's going on in the data. Numeric data can be continuous or counts, and we have different expected distributions for these. Okay? And again, we can use visual and numeric summaries. Text data is often a grouping or a class. And again, what we're interested in is group frequencies and counts, and we can use table summaries to examine these. But we can also examine not just individual variables, we can also examine how variables interact. And again, we've got a number of numeric and visual tools that we can use to explore the data, again with the aim of understanding the data structure, the patterns and the relationships in the data. We can use correlations and scatter plots for interactions between continuous variables. We can use correspondence tables to understand interactions between categorical variables. And we can use grouped summaries, box plots and so on, to examine the interactions between continuous and categorical variables. So really then, what this part of the lecture and the associated practical is all about is about understanding the data. What are the properties of my data? What are the distributions, correlations? What's the data structure? And again, part 2 of the practical undertakes these operations. You should go to part 2 of the practical now and then return to the lecture when you've completed this. So pause for the moment. The final part of the lecture is to determine whether the patterns and relationships that we observe in the data are significant in some way. And what we did in the last part, in part 2, was to examine data properties. We looked at single attributes, we looked at bivariate correlations between two variables, and we looked at group attributes as well. And some interesting correlations were found. There was a kind of relationship between shoe size and height and piercings. Actually, there's also an interesting relationship between gym time and the time it took you to complete the survey. And there's also some interesting correlations between social media time and the time it took you to complete the survey as well. We also identified some categorical variables that were correspondences between categorical data that were interesting. And again, perhaps what we want to know is whether the differences that we observe are significant. And we also looked at some kind of sort of category numeric interactions, where we looked at the differences across different groups, and whether, for example, mean height. We identified that height was different across different groups, and perhaps what we want to know is whether those differences that we observed are significant. Okay, so this is really what we're going to do in this part then. So we've identified some relationships that are potentially interesting, and what we want to know is whether these are saying something that's significant. And recall that in statistical terms, significance is a measure of surprisingness. Are these relationships that could occur by chance? Okay? And this leads to the null hypothesis. Now, the null hypothesis can be a bit difficult to get your head around, but essentially, what it says is that there is no relationship between factor 1 and factor 2. There is no relationship between height and piercings. There is no relationship, there is no difference in the measured values of height between male and female. Or that when we're comparing groups and groups, that they are the same, that the counts that we get across different groups would be expected to be the same. So what our statistical tests do is help to disprove or not the null hypothesis. And if we can disprove the null hypothesis, we say that if we're saying, well, actually we can't say there's no relationships, what we are implicitly saying is that there is a relationship. So this practical, part of the practical and the lecture, explores 3 statistical tests. We use Pearson correlations to determine whether correlations are significant for numeric pairs of numeric variables. We use student t-tests to determine whether there are significant differences in values across groups. So this is categorical to numeric. And we use a chi-squared test to say whether there are significant differences in counts between groups for categorical to categorical comparisons. So here, if you look at the bottom right here, we see there's an interesting trend here, whereas like left-handed respondents, all of the left-handed respondents, of which there were 9, do not use eyeglasses or contact lenses. Okay, now, is this something that we'd expect? Is this something that is expected statistically? Is this significant? This is a really interesting relationship. But what we want to know is whether that relationship is significant. The difference between male and female is really obvious and really large. But is this difference something that could occur by chance? And similarly with height and shoe size. We've got a very, very strong relationship, and I fitted the line between the data points there, showing this is 0.756, this slope, and we can, the correlation is, the slope's a different value, and what we want to know is whether this observed relationship is significant as well. So if we look at correlations, what we're trying to do is determine whether that relationship between height and shoe size is significant and statistically surprising. We can test the null hypothesis that it is not, that there is no relationship between them. Now, when we run the Pearson correlation test using the core.test function and the 2 variables, what this tells us is that it tells us what the correlation is again, but it also tells us that the p-value is incredibly small. Okay, and actually what this is saying is that this would not happen. Let me just work it out. Million. This would only happen by chance 1 out of 55,000 million times if data was drawn randomly. 1 out of 55,000 million times. So it's nearly 0. Okay, so this tells us that we can reject the null hypothesis of no relationship and accept the hypothesis that there is a significant relationship between height and shoe size. For the students' t-tests, we're examining differences across groups, and here we can look at height with gender. Now, we can see there are obvious differences. Are these differences significant? Are they statistically surprising? And we can test the null hypothesis that they're not. Now we use the t.test function, we put in the data, the relationship, and it tells us what the means are for the 2 groups. They're different, and they're saying that this is incredibly surprising. This would be found, let me just do my numbers here, only once in 8 million samples drawn randomly. It would only be found by chance once in 8 million times, 8 billion times. So we can accept the hypothesis that there is a relationship. And similarly, we can apply a chi-square test to examine the differences between groups, so categorical to categorical. And we were interested in this difference between left-right-handed with no visual support and glasses and or contact lenses, and we want to know whether this was significant and surprising. And again, we can test the null hypothesis that it's not. And here's the chi-squared test. We put our data in, and because we've got low counts in the groups, we put in the simulate.p value equals true, and that just does a bit of simulation, a bit of Monte Carlo simulation to help reinforce the statistic. Okay, and in this case, the p-value is 0.02, which is much less than 0.05, and that tells us to reject the null hypothesis again, and to accept the hypothesis that there is a relationship between handedness and the need for glasses and contact lenses. Now this time the p-value is lower than before, and it says that this is a relationship that you'd only find twice in 100 randomly sampled data. Okay, so if you drew data randomly 100 times, you'd only find this relationship twice out of those 100 samples. Okay, so the whole point of this part of the lecture and the practical is to introduce some statistical tests to test whether what you see in visual or numeric summaries is or isn't significant. Pearson correlations test for significance in the relationship between numeric variables. Students' t-tests test for significant differences in measured values between groups. And the chi-squared test is used to examine the correspondences between different groups and the counts between groups, categorical to categorical. The relationships are significant if they're statistically surprising, and really what that means is whether that relationship would be found from data drawn randomly and quantifying the extent to which it'd be found by chance. We used these statistical tests of the null hypothesis of no relationship between the variables, no relationship between the groups. And the p-values indicate the surprisingness of the observed relationship and tell us whether we can reject the null hypothesis or not. Okay, so in terms of the sequence, we've looked at the data. How good's my sample? We've examined the data and said, oh, there's some interesting trends there. And now we've done some tests of those trends to determine whether they're significant or not. Okay, and again, the RStudio practical illustrates these techniques. So the key things I'd like to take away from this part of the module are that we need to think about our data, we need to think about our sample, we need to think about the potential for bias in the sample and the representativeness of the sample, and that we can test that by examining the standard errors of variable means. And these give us an indication of how good our data are. Now, having determined how good the data are, okay, this is good enough for my use, we can examine the properties of the data using some summaries, looking at distributions, correlations, correspondences, and generally trying to develop an understanding of the data and structure using visual and numerical tools. Then, having found some interesting relationships, we can apply some statistical tests to examine whether those observed patterns, relationships and differences are indeed unexpected. Are they something we'd expect to find by chance or not? Now, these kind of principles, these kind of 3 stages, all relate to working with data in your future lives. At some point you will be given some data, and probably that data and asked to do something with it. And probably that data won't have been collected for the purpose you're going to use it for. So you need to do some evaluation of it. You need to be able to determine whether the data is useful for you and your problem or the task that the boss has given to you, or even your dissertation, as well as being able to answer the task. If you've done the practicals, then, and I strongly suggest that you do, then you will have picked up some RStudio skills. And just to comment that actually employers rate this, this is the most valued technical skill that you'll learn at the university. More than working with Excel, more than working with ArcGIS, more than working with QGIS, MapInfo, whatever. This is probably the most valuable technical skill you will learn at university. R&R Studio underpins the statistical work you'll do next year in research methods. So you will have to get to grips with it to pass parts, the modules next year. And to that end, please contact me if you're struggling. I can help set up some online classes over the summer or provide some tutorials that I think will be important to you moving forward into next year. Now, I've suggested some reading. It's all optional. If you wanted to go onto eBay or Amazon and get second-hand copies of these two books, then these are both excellent. I actually recommend the Harris and Jarvis book, and they probably have all the stats you'll ever need in your working life. There are some. I provided a link to some of the stats we've been covering today, a YouTube link to a very accessible summary from a South African professor, I think, and there's some online books as well. There's also a couple of practicals that you may want to look at that specifically reinforce the bits that we've been examining today in this lecture. Okay, so that's the end of the lecture, and your task now is to go and finish part 3 of the practical.